I did not receive any specific questions um, before I started, uh, and don't have anybody joining to me tonight, and that's perfectly fine. Apparently, there's some big basketball game going on, so I'm just going to go through like a sample test and talk through some of the things that I know people have had trouble with in the past. And some things that are kind of quirky on MyLabs Plus that people get wrong, not necessarily because they don't know how to do it, just because MyLabs Plus is kind of picky. And I'm recording this, obviously, so you can come back and just watch it at your leisure or rewatch it over and over and over again. So I hope this is helpful. And I did this for test number 2 because I didn't have a whole lot of videos in Moodle for test number 2. I did not do one of these for test number 3 because I pretty much had video lectures for every section in test number 3. But then again, here in test number 4, I didn't really have many videos made ahead of time. So I wanted to do this before you took your test for logs and exponentials. And again, like my email said, I'm going to have an on-campus review that's open to every student that's taking Math 171 this semester. So it's for the on-campus students as well. Most of them are going to be testing next week. We do Friday mini sessions, and I know I've invited you guys to them in the past. So this Friday, I am covering just a comprehensive review of logarithms and exponentials to get everybody ready to test next week on campus. And you are more than welcome to come. And because I'm not doing that until Friday, I'm moving the due date for this test from Thursday to Friday. That way, if anybody wants to come on Friday, you still have time to come to the review and then take the test afterwards. So I hope that helps as well. If anybody's able to make it, it's Friday at 10 a.m. in room 7115, which is on the first floor of the Science and Technology Center, right across the hall from the math tank. I'm also happy to set up a time in my office if anybody wants to ask any questions one-on-one or answer questions through email or over the phone or anything like that. So if you have any questions whatsoever, just get a hold of me, phone, email, however, come into the math tank, come to my office, and I'll be happy to help you. If these videos work, I'd be happy to make more of these videos. Just let me know. The last chapter that we're going to cover, chapter 9, is really, really easy. I'm going to be sending you some instructions. Almost everything can be done from your calculator. There's just one homework and then a test. And I'm going to send you some instructions on how exactly you can do everything straight from your calculator. So hopefully it'll be a nice, easy chapter to end with. Everybody can get end on some A's to boost your grades. So that'll be really good too. So in another screen here, I've got a little sample test opened, and I'm going to go through some of the questions. I'm not going to have time to go through every single question. And again, I didn't get any suggestions ahead of time, so I'm just going to go through the ones that I think are difficult, or I know that people have had trouble in the past. But if you recognize one that I scroll through and I don't cover it, just jot it down and email me about it, and I'll be happy to talk about it. So I've got a few screens here open that I'm going to switch to. And let me see. So we have got inverses. This chapter starts off with inverses and the domain and range of a function and its inverse. So we talked about domain and range all the way back at the beginning of the semester in chapter 1 and chapter 2, and we really haven't talked about it a whole lot since then. But I do want to do a quick little review of inverses and how the domain and the range of an inverse and its original function are related. So there's several ways to find inverses. Probably the most important way to find an inverse is through a function. If you're given a function, we want to find the inverse function. So all an inverse is when you switch the x and the y's. And that can be done from a lot of different formats. We can do it by switching the coordinates in a point. We can do it by flipping a graph over the y equals x line. We can do it by switching the variables in an equation or in a function. But really what it boils down to, no matter which format we're doing it from, we're just switching the x's and the y's. Which are our inputs and our outputs. And remember, the set of all of the x's that we're allowed to plug into a function make up our domain. And the set of all of the values that we get back when we do that make up our range. And if we're going to switch these guys, that means our domain and our range switch when we do our inverse. So the domain of f of x, that's the set of all the x's in our f of x, is going to be equal to the range when we find the inverse, because all the x's in the original are going to get switched to y's when we do the inverse. And then the range in f of x, all the y's in your f of x are going to get switched to x's when you do your inverse. So the range of your original function is going to be the domain for your inverse. So when you see this question, don't think of it as 4 things you need to find. It's really only 2 things you need to find. You just need to find the domain of the range of the original. And then when you do it for the inverse, you just take those same 2 answers and you flip-flop them. Because when we find inverses, we're just flip-flopping x's and y's. So to actually find an inverse, and typically we want to find an inverse function, which means we don't want to stop until we have our answer in function notation. So we just said a minute ago, finding inverse was switching the x's and the y's. Typically, we're given in function notation. So what I want you to do to start is to switch the f of x to a y. We actually need to see a y in the problem in order to switch the x's and the y's. Function notation, f of x is the same thing as a y. So we actually want to see the y in the problem in order to do this. And I'm going to go through an example in just a minute. Once we can actually see the y in the problem, we are going to change all of the y's to x's. And we're going to change all of the x's to y's. At this point, what we have found is the inverse relation. It's a relationship between x and y that we have switched the x's and the y's. But it's not a function yet. A function is always solved for y. So if we're asked to find an inverse function, after we switch them, we need to solve for y and then write it back in function notation. And what we've just done is found the inverse. So once we solve for the y, we want to replace it back with function notation. And since this is the inverse, we call this f inverse of x. And I'm going to go through an example here. And I'm also going to do the domain and the range. So let's say that f of x is the square root of x minus 3. F of x is the square root of x minus 3. We want to find the inverse, and we want to know the domain and the range for f of x and f inverse of x. So to find the inverse, our ultimate goal is to switch the x's and the y's and write it as a function. So right now, this has no y's in it. So that's why I said your first step should be to replace the function notation with a y. We actually want to see the y in the problem. Then it would make more sense to switch your y's to x's and switch your x's to y's. This, at this point, is the inverse relation, but that's not what we were asked for. We were asked to go all the way to the inverse function. So we've got a little bit more to do. We've got some algebra steps to solve. We want to solve for y and get it in function notation. So we want y all by itself. So we've got to get rid of the square root. So I'm going to square both sides. X squared is y minus 3. And then I'm going to add 3 to both sides. And I get y equals x squared plus 3. This is now our inverse function, so my final answer is f inverse of x equals x squared plus 3. That is our inverse function. We also want to find the domain and the range, and I'm going to start with domain and range of the original. And you can always do that from the graph. If you look at the graph of this function, it hits at the point 3, 0, and then it just goes up and to the right from there. So for domain, for the domain of f, if we scan this graph from left to right, it starts at x equals 3 and then goes forever to the right. So it's 3 to infinity. And then for the range of f, if we scan the graph from bottom to top, the graph starts at y equals 0 and goes up forever. So the range is 0 to infinity. For the domain and range of f inverse, we just flip-flop them. Oops. The domain of f inverse is going to be 0 to infinity. The range of f inverse is going to be 3 to infinity. And this is because to make the inverse, we switched all of the x's in the original to y's in our inverse. We switched all the y's in the original to be x's in the inverse. So all you have to do is flip-flop to find domain and range of the inverse. So this is pretty much everything that gets covered in section 1. Finding inverses, which you can do just with this simple set of steps here. If they ever talk about inverse relation, then you don't have to solve for y. You can stop as soon as you switch your x's and your y's. But if they ever use this function notation, then you have to continue solving it out for y and replace the y with f inverse of x. This is inverse function. And then for domain and range, you can just do domain and range of the original and flip-flop them for your inverse. There's quite a few problems that ask you to evaluate logs. And depending on what kind of calculator you have, this actually might be a really easy problem, or it might be kind of tricky. And now I'm not doing this in order, I'm just doing this in the order that they're coming up here on my sample test. And I'm just going to jump back to Google real quick and see if anybody is here. Okay. I just didn't want to miss anybody if anybody was here and was asking a question. So some of you that have a fairly new calculator might have an option under math that says log base. And when you hit that button, it gives you the option to type in a base along with the number that you're trying to find the log value of. This is only on the newer calculators. If you have that option, then evaluating logs is really, really easy. If you don't have that option, then you have to use the change of base formula so that you can use the two log keys that we have on the calculator. So if you've got an older calculator, you won't find a log base button. And the change of base formula says you can take any log, and I'm going to put some random numbers in here just so you can see how this works. Say log base 2 of 17. My calculator does not have a log base button or a log base option under math. So if I want to do log base 2 of 17, what I have to do is in my calculator, I use the log button on the keypad and I ask the calculator, what is log of 17? Now when I hit log of 17, a parenthesis opens and I have to make sure I close that parenthesis. And then I divide by log of 2. So the big number, and not that that number is going to have a larger value, but it's written bigger, goes in the top, and the base goes in the bottom. And then your calculator will tell you the answer. So log of 17 divided by log of 2. And my calculator says it's about 4.0875. 4.0875. Now it's not coming out to be a nice whole number because the way that logs work is they are the inverses of exponentials. And it's really important to know how to change back and forth between exponentials and logarithms. So when we want to solve an exponential equation where the variable is in the exponent, we have to use a logarithm to get it down and to solve. So these two are inverses of one another. These are inverse or opposite operations. Just like in beginning algebra, when we start learning to solve equations and we want to move addition from one side of the equation to the other, we use subtraction because they're opposite operations. Or if we want to move division, we use multiplication because they're opposite operations. Well, now we're starting to learn much more complex operations here. If we need to get rid of an exponential, we use logarithms. Or if we need to get rid of a logarithm, we use an exponential. They're opposite operations, just like some of that more simpler stuff. We can also rewrite an exponential equation as a logarithmic equation. And an example of this is 2 cubed equals 8. That is a true exponential equation. 2 cubed is equal to 8. And there is an equivalent logarithmic equation that goes with that. The base stays the base. So this is the base for your exponential. The 3 is your exponent, and the 8 is your answer. And I'm going to show you where each of these goes when we write it as a log. We can write all of this stuff as a logarithm. We would say log base 2 of 8 equals 3. So the base stays the base. The base in the exponential is the base of the log. And then the 3 and the 8 switch spots. Inside of your log, you put your answer. And then the answer to a logarithm, the answer that you're looking for, is the exponent that will turn a 2 into an 8. So anytime you're asked to find a logarithm, you're being asked what exponent will turn a 2 into an 8. It's an exponent of 3 that will turn a 2 into an 8. So the answer to a logarithm is an exponent. So the base stays the base, and really your other two numbers are switching spots. The answer is going inside, and then the exponent is moving to the other side. This is going to be really helpful when I talk about solving equations in just a minute, because one of the strategies for solving an equation is just switch the format that it's written in. Sometimes if your variable is up in the exponent, if we can just switch this to a logarithmic equation, all of a sudden that variable comes out of the exponent and we all automatically have this solved. We just have to be able to evaluate the left-hand log to find the answer. So the reason I went through this is to try to explain to you why log base 2 of 17 came out to be such a weird number. That's because there is no nice whole number that can turn 2 into a 17. 17 is not a natural power of 2. The powers of 2 are 2, 4, 8, 16, and 32. So 2 to the 4th is 16, but there is no nice whole number that's going to change 2 into 17. That doesn't mean we can't do it. That just means it's not a nice whole number. We have to ask the calculator to help us. So we know 2 to the 4th is 16. We're trying to get 17, so it comes out to be just a little more than 4, 4.0875. So the answer to a log is the exponent that turns the base into that answer. There is another log button on our calculator right below the LOG. And let me tell you what the LOG is. LOG all by itself means log base 10. This is called the common logarithm. It is the common logarithm because scientific notation uses powers of 10. To write really big or really small numbers, we use powers of 10. There is also an ln button, which is also a log. This is log base e. E is a number that you've probably figured out so far. E is the number 2 points, and I have to actually get the decimal right. 71828 ... goes on forever. This is called the natural logarithm. And there are a lot of things in science and nature that grow and decay exponentially based on this value, based on the value e. So that's why it's called the natural logarithm. So these two are very often given with no base written. And we just have to know, if you see log with no base, then they're talking about log base 10. And we have a button on our calculator for that. And if you see ln, that's log base e. Every other type of log, they're going to have to put a base in that spot. So this next question, it just says convert it to an exponential equation. It says natural log of 18 equals 2.8904. They want us to rewrite that as an exponential equation. So to rewrite this as an exponential, we need to know what the base is, because remember, the base stays the base. So a natural log has base e. So as an exponential, it would be e. And remember, the answer to a log is the exponent. And then this is the answer. So as an exponential equation, this is telling us that e to the 2.8904 equals 18. So be careful with the LOGs and the LNs. We don't always see their bases, but we need to know what their bases are. They're 10 and they're e. There's a few that I want to make sure that I get to. I have a review session for my trig class at 9. And I'm going to jump ahead here. This is definitely one that I want to do. Some of the application problems. This one says a doll sold for $263 in 1979 and was sold again in 1987 for $500. Assume that the growth in the value V of the collector's item was exponential. So we're dealing with exponential growth here. Exponential growth means we're using a formula that involves E. Find the value K of the exponential growth rate. Assume V sub 0 equals 263. So I'm going to show you what the exponential growth formula is and how you can solve for this. But we need to write down some of these values. So we've got a 1979 value. And we've got a 1987 value, and they're 263 and 500. Let's see. And the formula for exponential growth is V of t equals V sub 0 e to the kt. Now, different textbooks change the letters that they use, but they all follow the same format. V of t is stands for the ending value. Or there's a better way to write that. The value at time t. V sub 0 is initial value. E is a number. E is 2.71828. And don't ever type that into your calculator. There is an E button on your calculator that you should use. K is the exponential growth constant, exponential growth or decay. And we need to solve for that. If it's a value that's growing, K will come out positive. If it's a value that's decaying, which means getting smaller, K will come out negative. And then T is time. And time could be in years, days, months, doesn't matter. So we know two things. They tell you use V of 0 equals 263. And they don't tell you, but they want you to assume that means 1979 is times 0. Which means we need to figure out what T value to use for 1987. So if 1979 is times 0, you need to count how many years have elapsed from 1979 to 1987. And there are 8 years between them if you subtract. So T equals 8 is 1987. So they tell us to use 263 for V sub 0. So far we know V of T equals 263 e to the kt. We also know that when T is 8, this doll should have a value of 500. So I can plug those in. So it had a value of 500 when time was 8. Now, I've got a little trick that I like to use anytime I'm solving and there's a variable in the exponent. What I like to do is divide, change, divide. Divide, change, divide, and you'll have your answer. No matter whether you're solving for the K or the T, if you're solving for a variable in the exponent in these types of problems, you're going to divide, change, divide. So the first divide step is to get the exponential piece by itself. So we're going to divide over that coefficient. And this value is going to come out to be a really weird value. So you can either just leave it alone right now. If you do type it into your calculator, I suggest you leave the full value in your calculator and you do not round it. If you start rounding every single step of the way, it's going to throw your final answer off. All right, so I divided. My next step is to change this. And what I mean by change is to change it into a log. This is an exponential equation. So I'm going to change it into a logarithmic equation. That's going to pull our variable out of the exponent. So since this is an exponential with the base of e, I'm going to change it to a log with the base of e. And log base e is ln. When you change from exponential to log, remember those other two numbers switch spots. So now I'm going to have my answer inside and my exponent on the other side. So I changed it. Now this, I can type it in the calculator. Natural log of 500 over 236. That whole thing is just a number. And then the last step I need to do to solve for k is divide the 8 over. Now just be careful because the 8 is outside of the log. So we want to know what the natural log of 500 over 236's. And once we know what the natural log of 500 over 236 is, then we can take that answer and divide it by 8. And typically, let me see here. I'm going to check and see how many decimals they want. It says round to the nearest thousandths, which is 3 places. And on my calculator, 3 places would put my K value at 0.094. That's the first thing they wanted us to do, was just solve for K. So I've got to set up my equation. We've got to know the equation. They said use V sub 0 equals 263. They gave me a second set of values I can plug in for T and V of T, and then I divide, change, divide to solve for the K. This was just part A. Part B wants to now know what this function looks like. So in this problem, the V of T and the T are the variables. The other two are constants. Once we know their values, we plug them in and they stay in forever. So we know V sub 0 and we know K now. So V of T equals 263 e to the 0.094 t. That is our exponential growth function. Now that we know K, we plug it in and we leave it. So part B just wants to know what this function looks like. Find the exponential growth function in terms of t, where t is the number of years since 1979. Part C says estimate the value of the doll in 2013. Well, remember, 1979 is year 0, so we need to figure out what value of t represents 2013. So to figure that out, all we have to do is subtract them. 2013 minus 1979. And I get t equals 34. So for part C, I'm just plugging 34 in to my function for t. So 263 e to the 0.094 times 34. And I could type that entire thing into the calculator. Just be really careful. Depending on your calculator, you might actually want to leave these parentheses off and put a multiplication symbol in there. But you do want parentheses around that entire exponent. Anytime you have an operation in your exponent, you're going to want parentheses around it so that the calculator knows all of that stuff belongs in the exponent. So when I type this in my calculator, and we're talking about the value of a doll, let's see what it wants. It says round to the nearest dollar. So I got $6,426. That's a lot of money for a doll. I'm going to double check that. Yeah, that's right. Wow. And what is the doubling time for the value of the doll to the nearest tenth of a year? Doubling time. They want to know how long it's going to take for the value to double. So what does the value of the doll start at? The value of the doll starts at 263. So what's double that? Double that is 526. So they have a specific ending amount in mind. They want to know when will it have a value of 526. And we're trying to solve for time. Anytime you are trying to solve for a variable in the exponent, you are going to divide, change, divide. So I need to move my coefficient over and then change it to a log and then divide over my k value. So look what happens when we move that coefficient over. 526 divided by 63 is 2. That's because that's how I just found 526. I doubled to 63. So that's always going to happen. You're going to get 2 because we're solving doubling time. Oops. And then I'm going to change this to a logarithmic equation. So remember, the base stays the base. So I'm going to do log base e, which is ln. And then my other two switch spots. Right now, 0.094t is with the e. So when I rewrite it, 2 is going to be there. And then my exponent is my answer. And our goal here is to solve for time. So my last step is now to divide again. But remember, that last division is not inside of your log. We want the natural log of 2, and then once we get that answer, we'll divide by 0.094. And I got that time is approximately 7.4 years. The last question says, find the amount of time after which the value of the doll will be $4,250. We're going to solve this one exactly how we solved part D. They just gave us a different value to set it equal to. So 4,250 equals 263e to the 0.094t. We're just trying to solve for a different time now. We have a final value in mind. We want to know t. Anytime you're trying to solve for a variable in the exponent, you're going to divide, change, divide. So divide over your 263. That number is probably not going to come out to be a nice whole number. So you might just want to leave it as 4,250 over 263. You don't want to round it. So either leave it as 4,250 over 263 or keep the full decimal on your calculator to use in the next step. So there's my first divide. Now I'm going to change it to a log. So it's log base e, which is ln. My other two switch spots, so it's ln of 4,250 over 263 equals the exponent. And we're trying to solve for t. So now we're back to divide again. So divide by 0.094. And that last divide is separate from the log. So find your log value first. And once you have your log value, then you will divide by 0.094. So I got a t value of about 29.6 years. Let's make sure that's how they want this answered. Find the amount of time. Yes. So 29 round to the nearest tenth. So about 29.6 years. There's one more problem I wanted to do real quick, and it has to do with graphing. And I know quite a few people had trouble with it in the homework. It's this one. And I'm actually going to do this one on this screen. So the shifting we learned back in chapter 2. And most people were okay with the shifting. Anything that's inside of the function is going to move the graph left and right, and you do the opposite of what it says. So we're going to start with the graph of y equals 2 to the x. And then we're going to shift it left 4, because anything that's inside of the function, so that plus 4 is inside of the exponent, is going to move it left and right, and it's going to do the opposite of what you think. And then that minus 3 that's off as its own separate term, anything outside of the function moves the graph up and down, and you do exactly what it says. So that minus 3 is going to be down 3. So most people were okay with that. Where people messed up usually was with this graph. So an exponential graph, if you typed it in your calculator, you found that we use this button, looks like that one. And then if you click on the graph, it pulls up some options. You need to change the base down here from e to 2. We're dealing with an exponential function with the base of 2. So delete the e and replace it with a 2. And then we can tell it about our shifting. We did a horizontal shifting of -4. So move that to -4. And then we did a vertical shifting of -3. So move that to -3. So make sure that's on -4. Oops, sorry. Because I just said left 4. And make sure that one's on -3 because I said left 3. And make sure your base is correct. That's where everybody was going wrong in the homework, was they were not changing their base. Correct. Okay, so make sure you change the base in that pop-up window. The default is to make it base E. It's always going to want to do base E, and you're going to have to change it if your graph is not base E, which is probably not. It's probably going to be base 2 or base 3. So I only have another minute or two, and then I have to do a review for my trig class. This one you could just type it in the calculator. This one you could just type in the calculator. So the ones that I did not get to, this one is exactly like, well, yeah, this one's compounded continuously. Compounded continuously is exactly the same as exponential growth. You're going to use the exact same formula and do that one just like the doll problem. This one wants you to convert to a logarithmic equation. I've got that in the notes. This one is compounded quarterly. So this one's got a different formula. So let me go over and write that formula down real quick in case you don't have that. So anytime you are doing exponential growth or decay, or you are compounding continuously, they like to change the letters, but the letters don't really matter. It's the exponential. It's the one with the E. That's the formula you want to use. If they do any other type of compounding, so if they do compounded quarterly, compounded monthly, semi-annually, if it's anything but continuously, there's a different formula. It's A equals P times 1 plus R over N to the NT. And the only thing different in this formula is the N. That's new. The N is the number of times that you're compounding per year. So if it's compounded quarterly, it would be 4. If it's compounded monthly, it would be 12. If it's semi-annually, it would be 2. If it's semi-monthly, that means twice a month. So semi-monthly would be 24. So this is the formula for any other type of compounding. interest problem. The only ones I did not get to were the problems that involved the properties of logs and solving the log and exponential equations. But if you followed along with the application problem, then you might be okay. If anybody has any specific questions about solving the properties of logs or solving the logarithmic or exponential equations, I would be happy to make another video or answer your questions individually. I sincerely apologize. I scheduled another review session for my trig class at 9. So I'm going to go ahead and cut this one off and just let me know if you have more questions. I can answer them through email. I can meet with you in the math tank or in my office or make another video, and I would be happy to. So just let me know. I hope this helped a little bit. And again, I'm moving the test due date to Friday. And if anybody wants to come to campus on Friday at 10 a.m., I'm having an on-campus review session as well in room 7115.